In the early 20th century, physicists faced a profound mathematical collision. They had two successful, yet completely separate frameworks: the probabilistic mechanics of the quantum world and the strict geometric rules of special relativity. Unifying them was the ultimate prize. The baseline for quantum mechanics was established by Irwin Schroinger. His wave equation relied on a standard classical assumption: a particle's energy is equal to its momentum squared over twice its mass. But special relativity demands a different geometry. For a relativistic particle, energy squared equals momentum squared plus mass squared. Mathematically, taking the square root of that relativistic equation yields two branches: a positive energy solution and a negative energy solution. In a single particle framework, this implies a particle could continuously fall into infinitely negative energy states, releasing infinite energy, a scenario we do not observe in reality. Beyond the energy problem, forcing a single particle wave equation into relativity breaks causality. The math predicts a non-zero probability, but a particle can propagate across space-like intervals. It allows a particle to exist outside its own light cone. These flaws are restrictive. If the probability density is not strictly positive and localized, the predictive framework of quantum mechanics collapses. The single particle model cannot survive the rules of relativity. Paul Dirac formulated a brilliant first-order wave equation that bypassed some of the negative energy pitfalls and accounted for particle spin. Yet even the Dirac equation struggled to establish a strictly positive local probability measure, and it lacked a mechanism for the creation and destruction of particles. The common thread in these failures was the assumption that the particle, a single isolated point of mass, is the primary object of the theory. Physics found a different starting point: a continuous field, a mathematical value assigned to every point in space and time, stretching through the universe. Instead of trying to quantize the mechanics of an isolated particle, the objective shifts to quantizing the mechanics of this infinite field. This shift provides the mathematical degrees of freedom required to address the problems of causality and probability that broke the single particle model. To understand fields, we start with a grid of atomic nodes. Each node gets a mass, mu, connected by springs, kappa. The Lagrangian equation calculates the energy difference between moving nodes and the potential energy of stretched springs. This specific algebraic structure, kinetic energy minus quadratic potential energy, means our entire grid is functioning as a vast matrix of coupled harmonic oscillators. This reveals a core mechanical truth: any complex, continuous field can be reverse-engineered into a network of simple, interacting springs. To bridge the gap between our mechanical grid and a true field, we apply the continuum limit. We push the atomic nodes to infinity, shrinking the distance between them to zero. As the grid becomes infinitely dense, discrete summations are replaced by continuous integration. The discrete displacement variable transitions into a continuous field notation, phi of x. By carefully rescaling the mass and spring density parameters to absorb the infinities of this limit, the Lagrangian produces a specific equation of motion. This resulting formula is the classical Klein Gordon equation. By driving discrete classical mechanics to its absolute spatial extreme, we successfully generate a purely continuous, relativistic field. Analyzing the field in physical position space is mathematically unwieldy because the points are tightly coupled together. We need to isolate the field's underlying behaviors. We achieve this by applying a Fourier transform, moving our calculations into momentum space. The transform separates the interacting surface into a stacked array of distinct sine waves of varying frequencies. In momentum space, the coupling vanishes. Each frequency operates as an independent harmonic oscillator, corresponding to a specific momentum vector p. With the oscillators isolated, we execute canonical quantization. We swap classical Poisson brackets for quantum commutators, forcing the classical wave amplitudes to become operator-valued distributions. The smooth, continuous classical plane is gone. It has been transformed into an infinite, active set of quantum operators. This quantization introduces an immediate mathematical crisis when we attempt to calculate the baseline energy of the lowest possible state, the vacuum. This equation shows the quantum Hamiltonian, measuring total energy. Notice the zero-point energy term left over from the quantized oscillators. Evaluating a continuous field with an infinite number of oscillators per volume element yields an absolute infinity. But absolute vacuum energy has no observable physical meaning. Only changes in energy interact with reality, giving us the physical justification to redefine the baseline. We achieve this redefinition through a mathematical procedure known as normal ordering. It instructs us to manually restructure the equation by moving all creation operators to the left of the annihilation operators, zeroing out the infinite term entirely. By mathematically redefining what zero means for the vacuum, physicists bypass the infinities and secure a structurally sound, finite energy baseline. With the infinities removed, we arrive at the starting state of quantum field theory, the vacuum zero state, possessing strictly zero physical energy. This is the baseline of Fock space, a mathematical arena where the undisturbed vacuum is represented as a perfectly flat, motionless domain. When we inject energy into this system, we apply a mathematical creation operator directly to this zero state. The operator excites the underlying field, causing a sharp, localized wave packet to violently spike upward from the vacuum. This localized geometric field excitation carries defined momentum and strictly positive energy. It is exactly what human instruments register as a particle. Applying multiple creation operators generates complex multi-particle states, stacking layer upon layer of excitations to build out the mathematical architecture of Fock space. The implication is stark. Particles are not base physical reality. They are temporary, localized geometric excitations built on top of a field that fills all of spacetime. This framework directly addresses the paradox that broke single-particle quantum mechanics, the existence of negative energy solutions. Under quantum field theory, the mathematics are reinterpreted. Negative energy solutions no longer represent physical objects falling into an abyss. Instead, they are expressed through the annihilation operator. This operator functions mathematically to remove positive energy from a state in Fock space. When an annihilation operator encounters a particle state, the localized wave packet smoothly collapses back into the flat, motionless surface, vanishing completely. This means particle number is no longer a fixed universal constant. Particles can be dynamically created and destroyed based on the flow of energy. In this framework, matter loses its status as a permanent entity. The theory describes a universe where everything we measure, every electron and every photon, emerges from the activity of the field.